Starts. All right, I don't know where everybody else is, but it's 9 o'clock, so we're gonna go ahead and start. All right, good morning, everyone. So, just a reminder, real quick. So, don't forget that first exam is this Monday. Yes, this Monday. So, hopefully, we will finish with all the stuff today. If not, we'll take a little bit of tomorrow, maybe do a couple problems or something like that, and then we'll do a review, and then I'll give you time to work on the remaining of the group assignments, which are already posted onto Blackboard. And hopefully everybody saw my message, but I finally remembered to post was loud in my ear, the extra credit for test number one. Sorry, I've been a little preoccupied with all this car stuff, so I just kind of forgot about that. But it's up there. And Reinhard is going to remind me over the weekend to make sure I have those links and things posted for the extra credit as well as the group assignments because he's always on top of things and I always need a babysitter. So you're my chosen babysitter. You okay with that? Good. Okay. So let's bring us to today. As we start talking about yesterday, we have this thing called beats, right? So again, what a beat frequency is, again, I have same two tuning forks, but now I put the damper on here that creates a different frequency for each of these two tuning forks, okay? So again, I'm going to play both of them. And what I want you to do again is listen like we did last time. I've adjusted the frequency to make it sound a little bit better. But let's take a look at this. Sounded better. Perfect. Let's try it again. Yeah, you sound terrible. Just you a little bit. Okay, that should be fine. Okay. Right here, that a little bit better this time. Stop that. Do it again. So that wobbling sound is what we call the beat, right? So again, if you listen to it, you hear the whoa, whoa, whoa type sound. So in this case, you get a whoa, 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 whoa type sound. This is what we call the beat. That's a beat frequency. Now, again, this is called temporal because everybody in this room all hears it no matter where you are, which means it's not spatially dependent. But since it's going boom, 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 boom over time, this is why it's called a temporal interference. So what a beat is here's the schematic of this. So I have my two frequencies, so my two different waves with two different frequencies that are close in frequency playing at the same time. So since they are different, what will happen is as time goes on, these two might start off with a frequency so that the two waves are out of phase with each other. So that creates this destructive interference point here. But as time goes on, these two slowly become close to being in the same phase until eventually they'll be in the same phase with each other, which then gives me maximum constructive interference. And then they slowly become out of phase with each other again until they're maximally out of phase, which then creates that destructive interference, and then so on. Okay. So the whoa, 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 whoa sound you're hearing is actually this portion here from the point where it has destructive interference back to destructive interference. Okay, so that's what's creating this guy here. So ultimately, if I plot these two guys together and I do some math on that, what I'm not actually to do for you, but you get this type of thing here. So this portion here is the overall tone that you hear. So the overall tone, that sound that you hear, in this case, is the average frequency between the two. So this inside of this little packet here is the average frequency. So it's just the two frequencies added together divided by two. And then this part here is actually the beat. So this is what's called the modulation frequency, where the modulation frequency is what gives us this beat. So that's the portion that controls the whoa, 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 whoa sound that you're actually hearing. So that's the portion that is going to zero to maximum, back to zero, to maximum, back to zero, and et cetera. So this is what we call a beat frequency. Now, as I mentioned at the end of class last time, beat frequencies are used all over the place. So for example, in military applications, these are used in submarines. This is how you actually determine if things are stationary or if things are moving and what direction they're actually moving. So for example, if I had two submarines coming towards each other, you would send out a sonar, right? A pulse. That pulse then goes out, bounces off the object, and then comes back. If the two are moving, or at least the one that's coming at you is moving, you'll create this beat frequency. Right? From that beat frequency, we'll do some examples of that. You can actually determine both the direction and the velocity that that object is actually moving towards you. Okay? So this is one application of this. This is also used in medical applications. So, for example, this is how you determine the heartbeat of a fetus. So, when you have a woman who's pregnant, they put the ultrasound on her. The ultrasound, again, puts sound waves into the body. They then reflect back into the ultrasound machine. And again, when you have something like the heartbeat, you get it moving, which means you again get a Doppler shift. We'll talk about that in a second, which means that the reflected frequency that comes back is different than the original frequency, which again gives you this beat. And again, from the beat frequency, you can extract how fast it's moving, which allows you to determine the heart's rate, which this is. This is also, of course, used in music. This is the way that you tune an instrument, right? So if you play something like a guitar, violin, something like that, you have a tuner. So in this case, a guitar tuner. That guitar tuner plays the actual frequency at which it is that you're supposed to have. You strum your guitar for a particular string. In this case, if they're not the same, they have a slightly different frequency, you'll create a beat frequency. So in that case, you have to retune your guitar by changing the tension of the string to get rid of that beat frequency. Once that beat frequency goes to zero, then your frequency of your guitar, in this case the string, matches the actual frequency it's supposed to be, which allows you then to tune your guitar, right? Or whatever your instrument happens to be. So again, beat frequencies are used pretty much everywhere. Again, all it is I have two different, slightly different frequencies. And again, when I play the two of these, again, that wobbling sound that you hear, again, the overall tone is the average of the two frequencies. And then the wobbling portion is what's called this modulation frequency, which is what creates this envelope. Now, for our purposes, again, I'm not going to derive this, but all we need to know then is that the beat frequency is actually equal to the difference of the frequencies, which I'm going to write as the absolute value of frequency 2 minus frequency 1. Right. Sorry, I had to move you over there a little bit. So this is just what we call beat frequency. So beat frequency is simply the difference between the two frequencies. That's it. That's a beat frequency. So again, this is a temporal effect because again, everybody in this room hears it regardless of your spatial position. And it is simply that wobbling sound, which then changes as a function of time. Now, technically, some people in this room might hear it differently at their locations, but that's because we get reflections. So as the wave moves out, you'll get reflections from all the walls here because they are not soundproof, which means the reflected wave could give you interference in the spatial sense as it reflects back in, but we'll pretend that doesn't exist in this room, that it's soundproof or it's an open room, something like that. So, okay? So I'm going to postpone an example of this until we talk about our last topic, where our last topic is what's known as the Doppler effect. This is the last topic we'll talk about in this class. And of course, I wasn't smart enough to open the computer first, so I'm going to do that while I talk. So that'll be fun. So anybody know what a Doppler shift is or what the Doppler effect is? Go ahead.
It's something on the how the sound is moving relative to you.
Good.
Depending on the velocity, it changes pitch or frequency.
Exactly. So what it is an apparent shift in frequency. So this is an apparent shift in frequency due to motion. Exactly as Graham said. Right? So what happens is a source which is moving or a observer which is moving or both are moving will actually appear to hear a different frequency pitch. Mm-hmm. So let me show you a quick video of this. Once I open up my Blackboard here, there we go. Because again, I wasn't smart enough to do this at the beginning of class. Great. So again, there's three ways that this can actually happen. So let's talk about the three ways this happens while I open it up. So this can happen one of three ways. So number one, the source is moving. So giving an example of that, that could be, for example, a fire truck. It could be an ambulance. So if you were standing on the side of the road and you hear it moving towards you or away from you, you'll hear a difference in the pitch of the siren. Number two is that the observer could be moving. And then finally, the third one is, of course, a combination of the two. So for the second one, I could have a stationary source. So something like a speaker, which is playing something. And then I am moving relative to that speaker. Or the third one is I can, of course, have both which are moving. So for example, there could be an ambulance coming and I'm driving a car simultaneously. So in that case, I will hear that frequency pitch because I am in my car and I'm moving relative to this guy. So, all right, let's do a video of this real quick. Let me unplug this one and then we'll start this guy here. So it's just an example of this. So we kind of set up the frame here for you. So ultimately, all that's going to happen is there's going to be a guy playing a highly annoying note on a trumpet. Okay. And he's going to be playing that highly annoying notes in two different respects. One, we're going to see it from inside of the car, meaning that you're going to be moving with the person who is actually playing the notes, which means there's no relative velocity between the two of you. So you hear the actual pitch of the trumpet. And then the second part will be as an observer who's filming it from outside the car as the car is actually moving. Right? And all we want to do in this case is, of course, contrast the two different ones. Do we not hear anything? Can't hear anything. Of course. Let's try that. Okay, there we go. That's one of the most annoying pitches ever, but that's okay. So in this case, again, there's no relative motion. So even though the horn itself is moving, but the observer is moving with the horn, which means that there's no what we call relative velocity or difference in the speed between the two. So the whole system is moving together, which means that if Graham and I were in the car, I wouldn't notice Graham moving. Graham wouldn't notice me moving because we're moving together. Okay. Now, let's do it by the roadside, as this thing says. Okay. Okay. That's another version of it. So yeah, this is what we call the Doppler effect. So the Doppler effect, again, is this apparent shift in frequency due to the motion. So in this case, we have a stationary observer, we have a moving source, and that moving source, as it was moving towards the observer, how did the frequency of the sound when it was moving toward compare to the frequency of the sound when it was stationary? It was higher, right? So as it's moving towards it, you get an upshift in frequency. And then once it passed, what happens to the overall frequency? It went down, right? This is the same thing as if you watch NASCAR, right? In NASCAR, they show a stationary camera. The cars are coming towards them. It gets their down, and then once it passes through, so as it passes through. So this is the Doppler effect. So the Doppler effect, again, is just this apparent shift in frequency, where if it's moving toward, you get it upshifted. And if it's moving away, it's going to be downshifted as far as a stationary observer with a moving source. Okay. So let's use this idea and let's analyze and determine how is it shifted and what is the equation at which it is shifted by. So let's look at this guy. So let's look at the Doppler effect. And let's look at case number one, where we have a moving source. So it's going to be a moving source. Okay. So let's say at this instant in time, I have my source. So here's my source. And my source is going to be moving in this direction with some velocity v source. Okay. So then it's going to give out a pulse of sound, whether it be from that highly annoying trumpet, or it could be a siren or something like this. So this guy's going to give a pulse. So this is my wave crest here. So this is my wave crest. Now, we also know that the wave crest is going to move away from the speeding car or the moving source, whatever this thing is, at the speed of sound. Right, because this is happening in air. So this guy's going to propagate forward at the speed of sound, which means that at some time later, let's say a time change of delta t, which is equal to the period, this thing then is going to move out to this distance here. Anyways, okay? So I'm only talking about the sound wave in this case. So the sound wave was here. This is the initial pulse. And then in a time frame of a period, this sound wave then is going to move out to this position because it's moving at the speed of sound, where it now continues to move at the speed of sound. Everybody's doing okay? Now, in that same time frame, since the car is moving with a velocity of v, s, what's going to happen to the car? Is it still going to be at this position? No, it's going to move forward by some amount, right? So the car in this case is going to move forward by some amount. So it's now going to be sitting here. And then let's say this is some distance of x, where x is going to be simply the speed of this source times that time frame, or my time frame in this case is simply the period. Is doing okay? Now, once it gets here, because it's a period, it's going to send out another pulse. Well, that other pulse is going to now be something like this. Okay? Where this pulse now is going to be moving again outward at the speed of sound. Okay? Now, let's take the viewpoint of an observer. So if I was the observer standing here, right, what happens then? Well, what happens is what? If I was standing over here in a perpendicular direction to the speed of the sound, or at least the speed of the source. So if I was standing here, what I would notice is that in the time frame of a period, this wave would move from here to here, which means I would measure this as my wavelength, right? Because the wavelength is the distance between crests, which is also the amount of time that it takes here. So in one period, I would measure this guy as the wavelength. Okay. Now, if I'm standing in front, though, this now becomes my wavelength I would measure, right? Because what would happen then is I would first encounter this pulse, which is this pulse after a period. But now by the time I measure the second pulse coming at this time, it's now going to be a lot shorter, okay? So this guy here is what we call the apparent wavelength. I'm going to call that guy lambda prime. Okay? Now, contrast that if I was standing back here, what would happen in this case? So here, this pulse then would move to this position. But by the time I get the secondary pulse, this now becomes the new wavelength on this guy. I'm going to call that guy lambda double prime. Okay? So let me show you kind of a simulation of this so you can kind of see what it is that I'm talking about here. Because my pictures don't always do justice. Okay? So basically, this is what I would get, right? So if I have the moving source, right, it'll come back, and I'm the front observer here. By the time I receive the first pulse, the second pulse is basically right on top of it because it has given off the second pulse at a closer distance due to the motion. Okay? So now the wavelength that it should have, which is in the perpendicular direction, now becomes squashed. Okay? Simultaneously, on the backside, instead of as wavelength here, which it is that I should be measuring, I'm now measuring a much larger wavelength. Okay? So it's this shift in wavelength due to the fact that it's moving, where in the front side they get squished together, and on the back side they get elongated, is what ultimately changes the frequency. Okay? So this is where this apparent shift in frequency actually comes from. Right? So let's talk about these two different sides and what that ends up doing for our change in frequency. So let's look at the in front, or the front observer. So the front observer measures an apparent wavelength, which is given by lambda prime. Okay. Now, what we also know is that lambda prime must be, by definition, the same thing as what? The speed of sound divided by the apparent frequency. Right? And this comes from, again, the fact that the velocity is equal to the wavelength times the frequency, which means the wavelength is simply equal to the velocity divided by the frequency. So because they measure this apparent wavelength, that then gives them this apparent frequency. Okay? So now what? Now, we also know that this wavelength here is simply going to be the distance between the distance that's what? This pulse travels, i.e. this wavelength here, minus then the amount at which this car has traveled. Okay, so in this case, we can now rewrite this also as the distance or the actual wavelength minus then the distance x at which this guy travels. Okay, this is also our apparent wavelength. Now we also know our apparent wavelength is going to be the same thing then, or the actual wavelength will be the speed of sound times the period. Good. And then minus the velocity at which the source is moving times then the period. Is okay with this? Now the periods are the same, so let's factor out the periods. I'm going to get the speed of sound minus the speed of the source, all times the period. Now we also know that the period is related to the frequency by 1 over. So the period is equal to 1 over the frequency, where this is the actual frequency. So this then is going to be equal to the speed of sound minus the speed of the source, all divided by the actual frequency. Okay. So what this does now is it gives us a relationship now between the actual frequency, which is being played, or what is ever given off as the actual source, related then to the apparent frequency, which the observer hears. Okay with us? So now if I invert both of these and then multiply by the speed of sound, what I can finally find then is that the apparent frequency heard by the observer is then equal to the actual frequency times the speed of sound divided then by the speed of sound minus the speed of the source. So this is the apparent frequency for the observer in front when the source is moving toward the observer. Okay. Now, if it was moving away, so if the observer now is moving, or if the source is moving away from the observer, hence the back observer here, what happens in this case then is now the only difference is instead of this apparent wavelength now being the difference in these, it's now going to be the sum of the two, right? Because in this case, here is my wavelength given from the actual source itself, plus this extra amount at which the car is actually moving. So the only thing that's different between this one and this one is now I get simply a plus sign here when it's moving away from it, which means when it's moving away, we're going to get an apparent frequency, which is then equal to the actual frequency times the speed of sound divided by the speed of sound plus the speed of the source. Right? Because again, the only difference is now I've elongated it by this plus sign. Everyone's doing okay? Kind of makes sense. Now, before we move on to case number 2, let's look at some interesting things about this. And let's talk about why this thing makes sense. So number 1, our observation from the video was that what? When the car is moving toward the observer, the frequency was shifted upward. Right? So does that make sense here in this mathematical expression? Does that actually make sense? Does that correspond to our mathematical expression? Graham says yes. Yeah. Why, Graham?
So we're taking the speed of sound divided by the speed of sound minus the speed of the car. That means that has to be lower than the speed of sound. So you're essentially just multiplying by 1 point something usually.
Exactly. So something greater than 1. Exactly. So what happens in this case then is exactly as Graham is saying. So the bigger the speed of the source is, the smaller this denominator becomes, which means that when you're taking a number divided by a small number, this fraction here then becomes larger than 1. Right? Since this fraction is larger than 1, that then forces the apparent frequency to be greater than the actual frequency, which is why it's upshifted. Okay, so this results in an upshift in frequency. Now, in this case, it's, of course, this is the opposite, where when the speed of the source is taken into account, this now becomes bigger than the speed of sound, which means in this case, this is now going to be less than 1, which means then the apparent frequency will be less than the actual frequency, which is the downshift that you heard when it moves away. Right? So this guy now becomes downshifted. So these guys make sense, right? Based off what we saw in the video. Now, the next interesting thing I kind of want to point out is what happens when the speed of the source approaches the speed of sound? What happens in that case? Go ahead, Gabby. Exactly. So what happens is as the source approaches the speed of sound, my frequency becomes infinite. Okay. Now, what happens to the size of the apparent wavelength? Goes to zero, right? So what ends up happening is, and that's actually what the next simulation on here shows, is as the speed of the source approaches the speed of sound, the parent wavelength between the two collapses, which means that there is no apparent wavelength. It simply goes to zero. So in this case, the frequency actually diverges and goes to infinity at this stage. So for example, this is when a plane is flying at Mach 1, right? Mach 1 simply means it's moving at the speed of sound. Now let's go a little bit further. What happens when it moves faster than the speed of sound? What happens in that case is actually this. So what happens in this case is by the time it gives off the secondary pulse after it has already given off the first pulse, the secondary pulse is actually beyond the distance at which the first pulse has traveled. Which means in this case, it goes in front of it, which actually creates this interesting cone-like effect. This is actually what we call a shock wave. So the shock wave is what actually gives you the sonic boom that you would hear when you encounter, like, say, you go to an air show, right? And then you see the plane go like flying by, and you hear nothing, and then all of a sudden, a little later, you hear that, right? And the ground is shaking and everything's shaking. That's this effect. It's when the plane itself is going faster than the speed of sound, which then creates this cone. Because every secondary pulse is given off after the primary pulse. So it's given off in front of the primary pulse, I should say, which then creates this cone, right? So this is the cone that you would create. So in this case, the cone, if you see it, it's actually given there by an optical effect. So what's actually happened here was creating the sound is that the plane is moving so fast, it's actually ripping the air molecules apart. And as it rips the air molecules apart, this is the sound you hear from the air molecules themselves being ripped apart. Now, because you're ripping the air molecules apart, you're massively changing the pressure around the plane. So as the light comes in and hits this section, it's because of the change in pressure, which is causing it to diffract in different locations. So it's a trick on the eyes, which is why you actually see this, right? But this is also why you hear the whip. Like if you take a whip and you snap it, it's because you're ripping apart the air molecules at the end of it. So it's traveling actually faster than the speed of sound. Or if you take a towel, right? Let's say you want to straighten out your towel and you snap it. That snapping that you hear, again, is that the very tip of the towel is moving faster than the speed of sound. So you're ripping apart those air molecules, which again is what gives you that sound. Right? So these are the most interesting things basically about this. When I have a moving source, that moving source, again, as it approaches the speed of sound, the frequency will diverge to infinity, which means the apparent wavelength is going to go to zero. And if it goes faster, you create this shock wave or this cone-like effect behind it. Okay? But ultimately, we don't care too much about those. What we really care about is this is then the apparent frequency when it's moving towards, so the source is moving towards the observer, and this is then our apparent frequency when it's moving away. So next up, we then have case number 2, where case number 2 then is a moving observer. So let's look at that one. So let's look at a moving observer. So let's say we have a stationary source. So this is a stationary source. So here's my source, which means the velocity of the source is equal to 0. So this guy then is giving off wave pulses at some apparent or at some frequency. So here's some of my wave pulses moving out so that these are at some fixed wavelength. Now, let's say I have an observer. Here's my observer moving in this direction with some velocity VO for the observer. Now remind ourselves that this wave, though, is moving outward here at the speed of sound. Is okay with that? Now, what is this guy going to see? So this one now wouldn't see an apparent wavelength because what? The wavelength between each pulse will stay exactly the same. But what he does notice is, though, does he notice the wave moving at him at the speed of sound or at a different speed? So what I mean is let's say you're traveling down the void. You're doing 80, right? Because it's a void and everybody is 80, right? There's a car coming at you in the opposite direction, hopefully on the other side of the road. So you're not going to have a dead on collision, right? They're also doing 80. Now, when you're driving, in your brain, because you don't feel an acceleration, you think you're stationary. The only reason you know you're moving is because everything else around you is moving and you see the speedometer. But if you were traveling in a complete vacuum, for example, nothing's around you and you're traveling at a constant speed, you would never know. Okay with this? So when you see that car coming at you and you think you're stationary, how fast do you see that car moving at you? What's that? 160 miles per hour, right? Because now it's the sum of the two velocities because they're moving towards each other. Okay? Now, contrast if you were doing 80, or let's say I'm doing 80, Graham's doing 80, we're driving right next to each other. Do I see Graham doing 80? No, I see him doing absolutely nothing, right? But now let's say I'm moving away from him. He's moving forward at, say, 50 because, he's an actual responsible driver, right? Anybody actually know what the speed limit of the void is? 50, great. Seems like nobody actually knows that. But he's doing the speed limit, and I'm a jerk, and I'm doing 80, right? So if I'm going away from Graham, how fast do I see Graham moving? 30 miles an hour in the opposite direction, right? This is what we call relative velocity. So what's happening here is that this observer who's moving towards the sound wave will actually see the velocity of the sound wave at the velocity of sound wave plus his velocity at which it is that he's moving. So according to him, the velocity moving in this direction is be the sum of the two of those. Okay? So that means then that's what? The wavelength that he sees will then be equal to the apparent speed of sound divided by the frequency. Mm-hmm. Now, in this case, this should be the apparent frequency because that's what he thinks that he moves at, right? Now, we know the actual speed of sound is going to be the speed of sound plus then the speed of the observer divided then by the apparent frequency. But simultaneously, we know this side then has to be also equal to the speed of sound, the actual speed of sound divided by the actual frequency. Because the wavelength itself is actually determined only by what's happening with the source here. So again, all I have to do now is multiply this side by this, multiply this side, divide by the speed of sound. So finally what I get then is that the apparent frequency is then equal to the actual frequency times the speed of sound plus the speed of the observer divided by speed of sound. So this is the apparent frequency when, again, it's moving, or the observer is moving toward the source. Now, the only thing that's going to be different is when he's moving away from it. So now when he's on this side here, moving away, so the velocity is actually in this direction, speed of sound is still in this direction. But as we just talked about, the speed he's going to see the wave then is just going to be the difference in his velocities. Okay? So in this case, when it's moving away, the apparent frequency then is going to be equal to the speed of sound minus the speed of the observer divided then by the speed of sound. Okay. So this then is the apparent frequency when he's moving toward and the apparent frequency when he's moving away. Now, again, when he is moving toward, what does this say is going to be true about the frequencies here? Is it going to be upshifted or downshifted? It's going to be upshifted because now I'm increasing the size of the numerator relative to a fixed denominator. So this is going to be greater than 1. So this guy's going to be upshifted. And again, here, since I'm decreasing the size of the numerator, this guy then is going to be downshifted. So if you're moving away, this guy becomes then downshifted. Okay. Sorry? Oh, yeah, did I not draw the frequency? Yeah, same thing. Frequency should be that. Otherwise, that's a fraction, so it has no dimensions and it makes no sense. We all forget things sometimes. So what we actually call the Doppler effect is these two phenomenons put together into one expression. So in that case, we can have a non-stationary observer and a non-stationary source simultaneously. So we call them the Doppler effect. is just these two guys put together. So my Doppler effect says that my apparent frequency is equal to my actual frequency times the speed of sound plus minus the speed of the observer divided by the speed of sound minus plus the speed of the source. So this is actually the Doppler effect. So again, it's just these two scenarios added together into one expression, where again, if the speed of the observer is 0, we get what we did originally. If the speed of the source is 0, we now get what we just did. Okay? Now, two things to point out. Number one, the top signs here are when they're toward. So these guys are moving toward. And then the bottom two are both away. Now, the second thing to point out is how do I determine if it's moving toward or away? This is a scenario dependence situation. For example, let's say I have a car here and a car here, right? Let's say this one is my source. This one then is my observer. Now, in this scenario, let's say that my source is moving towards my observer. Simultaneously, my observer is moving towards the source. Okay? Now, whenever I have a scenario, I have to look at holding one of them 0 velocity and seeing what the other one is doing relative to that one. Okay with that? Which means that if I want to know the direction at which the source is traveling, I would pretend his velocity is 0 and see how is he moving relative to him. So in this case, what's happening as far as the observer is concerned with the source? If his velocity is 0. Is it moving toward or away? Toward, right? So this guy would be moving toward. Same thing here. If I say this guy is stationary, this guy is moving, is the observer then moving toward or away from the source? Toward as well, which means in this case, I would use both of these two top and bottom top signs. Okay? Now, let's contrast that with the same situation. Car here, my source, my observer. But now let's say my source is moving to the right. Simultaneously, my observer is also moving to the right. What is each one doing relative to the other one? So as far as the source is moving relative to the observer, is it moving toward the observer or away from the observer? Toward the observer, right? So this guy's moving toward the observer, because again, I'm pretending that what? This velocity is 0, so this guy's moving towards him. Simultaneously, what is the observer doing relative to the source? It's moving away, right? Pretend his velocity is 0, he's moving away. So this guy is now moving away from the source, okay? So in this case, when I do this one, for the source, I would use the negative sign. Since the observer is moving away, I would also use the negative sign, okay? So each one of these problems that you do, you'll have to take into account what is one doing relative to the other one, and that's what determines the size, okay? So again, best way to do that is pretend that the velocity of one of them is 0, and then see what the other one is doing relative to that, okay? So let's use that. Let's do an example. Let's do our first example. So our first example says that we have a police car moving at 80 meters per second, so roughly 150 miles per hour, chasing a speeding car, which is moving at 45 meters per second, so roughly around like 85 miles per hour, right? In the same direction as the police car. So we're talking about this scenario here. So let's redraw our picture here. So here is my police car. So this guy has his siren on top, right, giving off a frequency, moving in this direction with the observer, the source, which is equal to, 80 meters per second. Simultaneously, we have our speeding car here. So this is our observer. This is our source, moving in this direction with the observer, which is equal to 45 meters per second. And let's say the frequency of our police car siren is 800 hertz. Right? So all we want to know in this case is something simple, which is what is the apparent frequency heard by the by the observer? So what is our apparent frequency heard by our observer in this case? Okay. So again, here we know we have both a source and an observer moving. So that means our Doppler effect is going to be equal then to our frequency. Speed of sound, speed of the observer, divided then by the speed of sound, speed of the source. I'm leaving out the positive signs and the negative signs because we have to then, again, determine that by what's happening in the problem. Again, that's just simply this guy. So again, I know if I pretend this guy's velocity is 0, this guy's moving towards him. If it's moving towards him, we know the source then is going to have a negative sign because moving toward is the negative sign. Pretend this guy's velocity is 0. This guy's moving away. So this is going to be moving away, which again gives me a negative sign. Okay. Now, in this problem, since I didn't give you a temperature, let's pretend that the speed of sound in air, at least for this problem, sound, if I knew how to write, is equal to, I don't know, 343 meters per second. So let's take that as our velocity in this case. So good, so let's plug that in. So it's going to be 800 hertz times then, what, 343 minus then the speed of the observer, which is 45, divided then by 343 minus the speed of the source, which is then 80. So overall, is this going to be upshifted or downshifted? It's going to be upshifted, right? Because ultimately, we know that because the source is moving faster than the observer, which means overall, this guy's going to be moving towards him, which means it has to be upshifted. Okay. Mathematically, of course, the way we know that is because the denominator is going to be less than the numerator, so it's going to be greater than 1, so it's going to be upshifted. So plugging my numbers, what I should find in this case is this works out to be 906.46 hertz. So indeed, this guy is actually upshifted. Fantastic. How much time? Oh, I got 8 minutes. Great. So I got one more. This one's a little more complicated. So this one is actually going to involve both beats and Doppler effects. So let's talk about how this one actually works. So this one says that we have a truck attached to a platform. So let's say, here's my truck. Great. It's a terrible looking truck, but there's my truck. Okay. Move my tire more to the back. And let's say it's moving this way. So this is the bed of the truck, if you can't tell from my terrible drawing. Okay. So let's say the truck is moving in this direction. So this has velocity v of truck. That's then attached to a platform. So here's my platform. Put some tires on my platform here, which have 2 speakers. So I got one speaker in the front, one speaker in the back. They're both playing the same frequency, where the frequency at which it is that they're playing is 440 hertz. Well, that's you. Okay. Now let's say you are an observer standing in the middle of the 2 of them at this moment. Okay. Now, what's going to happen if I'm standing in between the 2? So let's think about what's happening here. So as far as my observer, which is this guy, who is stationary, what is the direction at which this source here is moving relative to my observer? Is it going to be upshifted or downshifted? It's going to be downshifted, right? So this one is moving away from him, which means he's going to hear a frequency from here, which is downshifted. Okay. Simultaneously, is this one moving toward or away than the observer? It's moving toward, which means is that going to be upshifted or downshifted? Upshifted. So what's going to happen then is this person in here is going to hear 2 different frequencies, because as this one moves and gets to him, it's going to be Doppler shifted. I'm going to call that F left, where F left in this case will be less than the actual frequency. Simultaneously, he's going to have a wave coming in this direction from him, but since it's moving toward, I'm going to write that as FR coming from the right-hand side, where FR will be greater than the actual frequency. So it's upshifted. Now, if I have 2 different frequencies coming in, what is he going to hear? He's going to hear a beat, right? Because as we talked about in the beginning, he now has 2 different frequencies. Those 2 different frequencies are going to interfere temporally, which means he's going to hear a beat. So this is going to result in a beat frequency where the Beat's frequency in this case is simply 10 hertz. Now, from this information, what we have to determine then is the speed of the truck. How fast is this truck moving? So from this given information, what then is the speed of the truck? Okay. So notice I have two different things simultaneously going on. I have two Doppler shifts and I have a beat. Now the beat in this case will simply be the difference between these two Doppler shifted frequencies, right? So let's start that here. So we know that our beat frequency is equal to the difference between the right and the left Doppler shifted frequencies. Everybody's doing okay? And I'm writing it this way because I know that this is upshifted, so it's greater than this one, so it's going to be a positive number. Okay. Next thing is, we also know these guys are Doppler shifted, so they're going to satisfy the Doppler effect. So this guy then is going to be the actual frequency. Now, in this case, my observer is stationary, so this is going to be 0. So I'm going to get the speed of sound divided by speed of sound, speed of source, minus the frequency times the speed of sound, divided then by the speed of sound, speed of the source. Now, in this case, what's the speed of the source? Well, the speed of the source is simply the speed of the truck, right? So in this case, I'm going to replace my speed of sound, or sorry, speed of the source with simply the speed of the truck, because that's what I want at the end of the day. Now, next thing next is I have to determine these signs here. Now, in this case, it's moving toward. So according to our Doppler shift here, if it's moving toward, is that going to be a plus sign or the negative sign? Negative sign, right? This one then is moving away. So according to our Doppler shift equation here, is that positive or negative? Positive is the opposite of this, right? So this guy's then going to be positive. All right. So let's factor out the FV sound. So this guy's going to be the same thing as what? The actual frequency times the speed of sound times 1 over the speed of sound minus the speed of the truck minus the speed of, 1 over the speed of sound plus the speed of the truck. Now, our job, of course, is to simply find the speed of the truck. So first thing I'm going to have to do is combine these two guys together by finding a common denominator. Common denominator, of course, is just the product of these two. So let's do that. So this guy's going to be the same thing then as the speed of sound times the frequency times then, I'm going to cross multiply. So this guy's going to go here. So I'm going to get the speed of sound plus the speed of the truck minus then speed of the sound minus the speed of the truck, all then divided by the speed of sound plus the speed of the truck times the speed of sound minus the speed of the truck. Okay. I don't need this anymore, so let's get rid of it. Okay. Now let's look at the numerator. So in the numerator, I have a speed of sound here with a minus speed of sound here. So what happens to the speed of sound? We're going to cancel. So this guy cancels with this guy. Here I have a V truck, but then I have a minus V truck. But what's a minus V truck? Positive. So they get this guy with this guy, which gives me a 2, right? So I get my B frequency. It's going to be the same thing as then 2 of the frequency, the actual frequency, times the speed of sound times the speed of the truck, divided by the product of these two. Well, the product of these two, because one's positive, one's negative, the cross term is going to cancel. So in this case, I'm going to get simply the speed of sound squared minus the speed of the truck squared. It was okay? Now, because I want the truck, from here, I'm going to, of course, cross multiply. I'm going to bring this term over here. I'm going to divide by this term, and then we're going to rearrange to get speed of the truck. Well, let's get everything on one side. Let's do it in baby steps. Okay, so I'm going to get speed of the sound squared minus the speed of the truck squared is then equal to 2 times f times speed of sound divided by the beat frequency times the speed of the truck. But now let's bring these two terms to the other side. So finally what I get is the speed of the truck squared plus 2 times the frequency times the speed of the sound divided by the beat frequency times the speed of the truck minus the speed of sound squared is equal to 0. So what do I have to do to find the speed of the truck? What do I have to use? Everybody's favorite thing on the planet. So quadratic. So we have to use a quadratic equation because this thing comes in with a quadratic and a linear. So if I do that, what I finally find then is the velocity of the truck is 3.9 meters per second after solving that expression. So that's it. We're completely done. So we did finish everything today. Fantastic. So tomorrow we'll start off with a review. We'll go through what type of questions that we're going to expect, which I haven't made the questions yet, so that's going to be hard. So I have to think about that today. Other than that, the rest of the time, I'll give you time to just work on those group assignments that are remaining, let you ask questions, or you can just leave after that. You'll break my heart, but it's okay. We'll get there. So, was okay?
I'll be there the whole time.
You have no place to go. So. Should say you have no place to go, but
The place I have to go is also.
Exactly.